everybody, welcome to our first talk. Our first speaker today, Charles Lohr, pulls off a lot of incredible hacks. And by incredible, I mean literally incredible. Sometimes they border on the nearly implausible. My favorite example of this was he worked out a way to get Ethernet out of the ESP8266 chip by basically bit banging it. And we wrote this up, Ethernet interface discovered in ESP8266, and we published this on April 1st. And you can imagine what antics ensued. That was really, really fun, but it was real. So it's my extreme pleasure to introduce to you Charles Lohr. So please welcome to the Hackaday Supercon stage, Charles.
Hello. Let's see if we can get this up there. Just FYI, if you're interested in following along, or if you'd like to be able to see any of the references, the link to the talk is right there. It's just a web page, but you'd have to swipe left and right to switch slides. So if you're curious, just go take a shot at that. All right, so who here is here to learn about how to use the radios that you get in microcontrollers like the ESP8266, ESP32, or like one of the Nordic chips? Who here is here for that? You're in the wrong place, because this is about using the chips that don't have radios or just doing other stuff than using those radios. Who am I? I am Cian Lohr. I'm a YouTuber. I've got this YouTube channel, but you can see I probably only output maybe like one video or one or two a year. I'm much more active on GitHub, where I've got 187 repos, and you only get to see the ones that are public because those are the projects that worked out, and you don't get to see all the ones that are still private there. So if you see the little Jesus fish anywhere on GitHub, it's probably me. And I love exploring what microcontrollers are capable of without wads of abstraction. So like if we just take the hardware and we write some code and we don't just have layers upon layers of abstractions, what can we do? So microcontrollers are basically just tiny little computers. They run code, but they also have I/O, so they can affect the real world. It's usually a really basic CPU, anywhere between 8 and 32 bits, and 1 to about 240 megahertz on some of the higher-end microcontrollers. Unless you put an ESP32S2 in liquid nitrogen, then it kind of cooks up to around 960 megahertz, but we're not talking about that today. The big thing that I want to know with microcontrollers is, like, can I write software to do things like talk Ethernet, like with ESP-Ethernet, again, released on April 1st, which I don't think I'll ever do that again because most people thought it was a joke, or communicate over USB. So this is a little CH32V003, the same kind you have on the Swag, doesn't have a USB interface. It's only 8 cents, but that doesn't stop us from talking USB with it. Or maybe becoming a power supply, like a high voltage power controller for a Nixie tube. So no dedicated controller chip, but absolutely able to go make a nice 160 volts for the Nixie tubes. Or broadcast FM radio through some touch pads. Maybe even transmit some video over the air. Or later on in the talk, like just earlier this year, me and a friend, we were able to actually send LoRa packets out, chips that don't have radios. And let's see if at the end we might be able to receive some radio signals. So I have a set of rules that I follow when I do all of this. So my goals are, I don't want to use extra hardware. I'd like to just take a dev kit and just run with it. Things that are common to most microcontrollers are totally fair game. So using the SPI bus or using an ADC, maybe a timer or using DMA to pipe the data around inside the chip. Totally fair game, that's cool. Any extra components like resistors or capacitors, I start to get kind of like, well, what's the point if you have to actually like put on extra electronics? I want to be able to just do this just in software. Anything active like a transistor is right out, and in chips, like extra chips with dedicated features or like just not interested. That's something else you got to buy, something else you got to put on. No, I want to be able to get it cheap. And if we can get some thinking and write some code That's where I'm interested. And we're trying to write this so that it's something that the original chip designers would have expected is impossible. That's my goal. And the first chip that really caught a lot of my attention and inspiration is the ATtiny 85 and the ATtiny 45. They're these tiny little chips from Atmel. They're 20 megahertz, 8-bit, little tiny parts. Very simple, very basic. They have this neat feature where they have an internal oscillator, so you don't need an external crystal. And there's a register. So if you write to this memory address, you can change the frequency of the part anywhere from about 5 megahertz on up to about 15 megahertz. Actually, I just realized I don't have my clock out, so I need to keep time. Okay. Sorry. Okay, next. So one of the neat parts, going back to it, so we can make a frequency, and that can be what drives the part, and we can control the frequency in software. And we can route that clock through the chip, through various things, however we want to hook it up. And one of those things is a PLL, and that can take that frequency that our internal oscillator is running at, and now we have 8 times that frequency to go play with. One of the first big projects that really inspired me was Sprite. Sprite used an ATtiny 45, and Sprite used the internal PLL. Sprite is a hacker that has shared this stage as well. And he wanted to see, what if we use no external parts or even pins? So he cooked the internal PLL up to 90 megahertz, and he successfully modulated FM.
Here and tuned to about 100 megahertz.
So now, mind you, this is no external components. This is just adjusting something inside the part, and the FM radio is able to hear the internal components inside this part glitching around. I saw this and I was like, okay, that's cool. That is the kind of stuff I want to do. But what if I want to transmit a little bit further? Well, the part has this neat thing here, this PWM output, which is normally used for just dimming LEDs. But what if we were to hook it up to this 90 megahertz source? Now, it's a little annoying because the only frequency we can get out is 1/3 of 90 megahertz, but that's okay because it's a square wave and we have harmonics. Now, I didn't actually know about harmonics before I started all this. I, in fact, played with it. I'm like, well, why is there a frequency there? And somebody had to explain to me it's because of harmonics. And what that means is whenever you output something like a square wave here, it's actually made up of a lot of other waves as well. So if you're turning a pin on and off and on and off and on and off at some frequency, what's actually being emitted, what's coming out of that pin is that frequency, a third or 3 times the frequency, 5 times, 7, 9, etc. And those are called the odd harmonics. And so when you turn a pin on and off with a microcontroller, you're creating a little bit of noise up the spectrum. Now, it's even less than that because there's slew rate limiting on I/O, so it's actually much very, very muted the further up the spectrum you go. But there is a little bit of power there, just a little bit. So this is a square wave coming off of an ESP32S2. It's going really fast, so you can see it's having a hard time keeping up. But you see that it generates the frequency at the frequency we're trying to generate. And it also generates a higher frequency, a higher frequency, a higher frequency up the spectrum. And that means that we can affect a signal that is higher than the highest frequency we can transmit at, or that we can turn a GPIO on and off. And one of the other neat parts is, if we do something shifty with the signal, the images also appear up the spectrum as well. And so using that knowledge, I decided to try to take Sprite's work and just hook it up to the output. So these 2 little touch
Maybe I have
pads.
to tune a little bit more. And right now, the funtenna on this ATtiny 85 is transmitting to this clock radio here. You can see that I can get it a long ways away, and it still transmits pretty well.
So that there is just 2 little touch pads on the MagFest swag that's able to just, instead of being touch pads, they are now turned into a little bit of a dipole, so to speak. So one of the other things to note before moving on is there are absolute ratings with chips, but they are just suggestions. So there's the safe operating region for an AT-Tiny85, and we're using it about up there. So totally works on some parts, not all, but it's okay because we're not going to be making it into a product, and we'll learn a little bit more about that later. One of the other things I absolutely love about the AT-Tiny85, and so this is if you guys wanted to get started with it, is it's really simple. So like to bring up the whole clock tree like I showed before, it's just these 3 commands. To be able to adjust the oscillator up and down, it's just set this value called OSCcal. And the neat part is you can just like set it to one number and set it to the number below, and now a number back and forth real quick, and you can actually get it to like tune to sub LSB values by dithering the value that you're sending in. And then the last part is to say configure it. So this is the difference between Sprite's project and mine, was just 4 lines of code to be able to output what was on the part. So we start building this toolbox. So we have a digitally controlled oscillator. We're going to be doing frequency modulation with that. We have the ability to dither a signal to adjust it really fine tune. We can use a PLL to multiply a frequency to a higher frequency. We can use a PWM, so like an LED dimming circuit, to output the signal to the real world. We can use harmonics to output frequencies higher than what we could normally transmit. So now using that, okay, I know all of this stuff. I've built some of my tools. Now I want to be able to transmit some NTSC video. And that's an old video standard. So I started with the AT-Tiny85. I know it's AM modulated, but there's 2 PWM outputs. So I could turn one off or the other off or both on in order to generate different amounts of power. And I need that because an NTSC video signal, sometimes you have to transmit very little power to sync. You have to transmit a little bit more to tell it like black. So sync tells it like where to shoot the cathode ray gun. Black says make it black, make the pixel black, or white, or anywhere in the gray, it's okay. But white says make this pixel white. It's only 3 voltage levels is all you really need, and that's cool because having the 2 PWMs, it's pretty easy to do 3 voltage levels. One thing, if you ever do want to do this yourself, just by the way, it'll save you a ton of time to just know this. When you transmit NTSC, it's actually flipped upside down in that like sync is the most powerful and black is less powerful, and if you turn off the output, it becomes white. Totally news to me. If somebody told me that, that would have saved me a good week worth of frustration. It's a much more complicated thing than just sending FM. It has to do with really specific timing, but if you follow all the timing rules, it totally works. So this is like a little wire antenna coming off an AT-Tiny85, broadcasting to that television right there. So a couple years later, the ESP8266 comes out, and I absolutely love this chip because it was the first time it was a really serious microcontroller for not a lot of money. So I get these boards, and I decided, okay, I want to be able to broadcast some video with it. It's got enough RAM so you can make like a frame buffer and do fun things with it. But it doesn't have any PWMs. And I was like, okay, well, how do you deal with that? Well, it does have this thing called an I2S bus, which is normally used for audio. And it can play back pre-programmed bit streams, and I can create a bit stream for each signal level I want to do. And sure enough, it absolutely just worked. So I was able to output black and white NTSC broadcast television, and that just worked. So now in our toolbox, we have 2 more things. We have amplitude modulation, so that now we can change the power that's in a signal to convey information. And now we also have the ability to use something called an I2S bus instead of just a PWM. And so now we can generate these custom bit streams and output them on chips that don't have a good structure for good PWM output for RF signals. Next, I wanted to add color to this. So it requires multiple signals now. So not just like black, white, and sync. Now we also want to have different colors. But there's no hope of keeping up when we do this. Like to be able to compute that on the fly on the ESP8266 was just way outside the scope of what it could do. But that didn't stop us from using LUTs, lookup tables, to be able to create a bit stream in JavaScript, store it off as like a little table that it just says like, look, if you just blast this out the I2S port, this little audio port, it's going to be fine. It'll just transmit the signal. But nothing I did worked. And I could not figure out why. I was getting all this confusing output where I'm like, no, I'm sending the signal, and the harmonic would be where I want it. Why is it not appearing there? I got an SDR, and none of the signals that I was seeing on the SDR were matching my expectations. So I wrote a simulator. This is that simulator right here, and I was able to eventually figure out what to do. And what it was it wasn't just a signal and its harmonics. It's a little bit stranger when you output through an I2S bus or a shift register. What ends up happening is you get the signal you're after, but it's mirrored around half of the sampling frequency and then repeated every sampling frequency up the spectrum. Now it's repeated, it's much lower power, every one of the harmonics, but it was still really helpful to write this little simulator which creates a bit stream and then runs a Fourier analysis on the bit stream to be able to see what's actually happening. And so I just wanted to make sure that's real. Is that really what's happening? And then sure enough, absolutely. When I looked up at 62 megahertz, even though I'm only able to output at most 40 megahertz, it's still having effects in the spectrum at 60 megahertz, and the simulator is matching reality, like almost perfectly. This is actually a capture I did before I did the talk, and it's shocking to see, like, the signals are exactly where you would expect them to be based on the simulated signal. And absolutely, it worked, and we were able to output NTSC color, NTSC video. Now, there's one funny thing that would happen is while I was working on this, a lot of times my connection to the ESPD266 would drop out. You can see the ping times going absolutely bonkers there. And it turns out that one of the colors was creating noise way up at 2.4 gigahertz, just a tiny little bit of noise, and it was right in the middle of Wi-Fi channel 1. Wi-Fi uses something called carrier sense multiple access. So if it senses somebody else talking on its channel, it doesn't care what it is, it's gonna hold off and not send packets. And in fact, it was holding off long enough in some cases that it actually disconnected from the Wi-Fi. So turns out there is a little bit of power there, and that's something that was sitting in the back of my head. So we added a few more things to our toolbox. Actually, I think it's just one here. We get reflections when we do direct sampling. So it's not just harmonics, it's all the wacky stuff with the reflection and the repeat up the spectrum. And there's this neat little trick. So if you look here, the neat trick is when you want to generate a frequency, you can just have a frequency you want to generate, simulate a sine wave at that frequency, and even though you're not able to like represent that sine wave, if you just sample where you would be outputting, you can put any number you want in there, and there will appear a tiny little signal where you put that. It'll have tons of other garbage all over the spectrum, but you can create a signal anywhere you want, and you can just bypass all the crazy math by putting in a number and simulating it out. All this was done here, and let's just, instead of doing a toolbox, let's call it a bingo card, because that's a lot easier to take with us. And so earlier this year, my friend Frank and I, we were like, okay, well, could we send LoRa? Frank was telling me about LoRa, this like long-range radio protocol, and he's telling me some really incredible things about it going a really long way on very low power and operating way below the noise floor, which means that if you're just a few feet away from a LoRa transmitter, you can't see the messages at all. But a LoRa receiver can, and that's through through the ability to process the signal and get gain that way. The other thing is this is at 900 megahertz, so we were operating down at like 65 megahertz or 90 megahertz, and those are things that we could actually generate reasonable things at. But up at 900, it's just the tiniest little bits of noise. These signals are only 125 kilohertz wide, so we have to have very good control over what we're trying to send. They're chirps. It's not even like FM or AM. It's this like very unusual protocol we'll see a little bit later. We're going from my experience with just this basic analog stuff to something that's much more sophisticated and digital with forward error correction, whitening codes, digital interleaving or diagonal interleaving, gray codes. We have to deal with the phases of various symbols. And my dad, who's a former physicist and electrical engineer, said you'll probably get about 10 or 20 feet, even with all of that like being known, because it's just so ridiculous. And if you're curious how we did it, I have a complete write-up here on my my GitHub page for it. So if you're interested in this sort of thing, you can do this or watch the LoRa video. But that is mostly outside of the scope of this talk. But what is inside the scope of this talk is what one of these basic signals look like when it's being sent by a microcontroller with no radio. So what ends up happening is time goes down this way, and you can see these tiny little chirps that help get a receiver sunk up. Then it says, oh, here's the start of the packet. And it sends the packet by sending little segments of these little up chirps that are just shifted in time in order to actually send the signals. So I started with trying to do this on an ESP32S2 because I thought, okay, well, I could make the little chirps by adjusting this thing called an audio PLL in the ESP32S2 and using a PWM output, but we just couldn't get it working. So then I moved to, well, okay, I have this other box in my other set of tricks in my box. Let's try to use an I2S bus or a SPI bus. So the CH32V003, 203, or ESP8266, okay, sure, let's give those a shot. They have that I2S bus, like I'm used to using before, and I made a bunch of tables that just mimic a chirp. And I wrote the whole rest of the LoRa stack. So that's all, that all works. And I wasn't able to get it working on the 003, but I did the other two. And so here we can see a little simulation of what a signal on the 203 would look like when you're shifting out at 72 megahertz. And it actually looks surprisingly clean. And we'll see a little later, it was able to be received. So by shifting the frequency around inside of the table generator, we are able to make a signal that'll exist up at 900 megahertz, even if it's really weak. Now, I think one of the two reasons it didn't work on the 003 was this, that when you're shifting out at 12 megahertz, which is all you can practically do on the 003, the signal looks like complete garbage. And so I guess that's just maybe some sort of limit that I was hitting. Maybe somebody else could do better, but I just couldn't push it on the little 8-cent microcontroller. But yeah, we were able to actually craft these messages and package them in this protocol called LoRaWAN, which was then received by a commercial LoRa gateway. These are the kinds of things that are in HVAC systems or whatever to monitor hardware. And it was able to send those packets from microcontrollers that don't have radios, or I guess the ESP8266, which does, but we're not using the radio, over half of a kilometer. So just by noodling this little thing, we were able to get packets to flow over half a kilometer, and those packets would be able to be forwarded around the world. I did draw an 003 here. It's not even that many pixels. It was pretty rough. And so for this, our little bingo card, we are using harmonics, an I2S bus, reflections, and yeah. So back on the 003, when I was trying to generate a tiny little signal from 904.1 to 904.3, it ended up just producing all of this stuff. And I think that that's for the biggest reason is that I don't think the SPI bus is cycle accurate. Now, when you're making an SPI device and trying to communicate on a bus, you don't care if the next transaction happens 1/48 millionth of a second later. But I do, so it just didn't really pan out. The other one to note is that there's a little quirky thing. So you're doing all this RF with the ATtiny85 earlier, and that's fine. And I'm like, okay, well, the CH32V, like what's on the badge here, also has an internal oscillator that's tunable, but it's a lot warblier. And I think that's on purpose to make it easier for people to make products that pass EMI and EMC. But one of my friends on my Discord decided to try to mimic a 433.9 megahertz signal, and you can see it's just really just garbage and spread out. So without a clock, it's a little bit tricky to do this at all, and even with a clock, probably not going to be going too far with the 003. So moving on, we wanted to just try again. We really wanted to try to get this working with the ESP32S2. So one of the things is, if you look at the signal here, we get the whole reflecting around, but what if we send the signal only at half of the sampling rate? So send a 6 megahertz signal with a 12 megahertz sampling rate. Oh, looks at that. They're harmonics evenly spaced up the spectrum, which is the same as if we just did a PWM output. So maybe we got a shot at this. So using all of the same stack as before, we decided to try again, and I was able to actually get the ESP32S2 to output on 2 of the GPIOs. and it blew everything else out of the water. And we were able to transmit packets, mind you, from this, it's like a little MagFest swag. It's like a badge like this, and just using the SAO port and plugging 2 little wires into it. We're able to send it on this drone to a receiver over 1.5 miles away, or 2.5 kilometers. Okay, yeah, sure. It was just wild that this worked. And I used to think that you needed to have like a cybersecurity degree. Oh, yeah, bingo card too. I used to think that you needed a cybersecurity degree to reach like this level of paranoia about things that don't have radios sending packets and spying on you and sending packets around the world through these other networks and all. No, it turns out all I needed to do was just play with microcontrollers and radios to get there. So I'm pretty good to go on that. There were 2 other little projects I wanted to mention before moving on to the second part of this presentation, which is shorter. One is the ESPD266 and sending 315 megahertz. So I decided to just, well, what happens if I do 315 and try to become a little garage door opener? Answer is it worked on the first try, and the distance was further than the official remote, using the same tricks in the box. The next one was, this is like future work that I really wanted to do. I really want to try to send Whisper with the ESP32S2. So I mentioned PLLs being a way to multiply a signal. The ESP32S2, not the S3, but the S2, has this special thing called an audio PLL, where it's not just like clock times one number over another number. It's clock times this really detailed thing where you can get really fine-tuned. And when outputting 40 megahertz, you can control the output frequency down to 30.581 hertz increments. Now, that doesn't quite get us to the 1.4648 hertz increments that we need to get at for Whisper, but it does get us close. So maybe we can pop on the dithering box and be able to get somewhere. My first attempt didn't work. It turns out there was a lot of biasing with it. But oddly enough, if I switched the way I was dithering to use pseudo-random noise, it actually did work. And I was able to get sub-hertz control out of the output of the ESP32S2. So now, this isn't doing Whisper, but maybe someday. The last part about this part I wanted to mention was there are unintentional radiators, and that's what I would love to be able to be. I'd love to be able to make a product that has no antenna, like no clear antenna, no radio hardware, doesn't have anything to do with sending signals, but then sends signals with them. Because it's actually not that hard to hit all of those rules and still be able to slip in enough stuff to be able to send a signal. But it doesn't work that way, even though that's not that hard. And I do want to note that like the amounts of power that we're dealing with are really low. Like a lot of the graphs where you saw the SDR readings, like the antenna was literally that close on the graphs, like on the one with the NTSC. So the amount of power we're sending is really low. It is possible. But and oh yeah, and even like 5 feet away, you can see like this signal here is a signal I'm making, and this is just in the FM spectrum. You can see distant FM stations able to just overpower it. But it comes down to the intent. And so the FCC is not going to be happy if you are intending to send radio signals with a device that's not intended. The other thing is, please do not put an amplifier on anything like this. It produces noise everywhere. And you're probably not even going to be transmitting somewhere you're allowed to transmit anyway. So please just don't do it, because the FCC is going to come and pound in your door, and nobody wants that. So let's move on. We're done now. I actually just got a ham license, so I'm a little bit cautious to send things I probably shouldn't be sending now. So let's move on to receiving. So when receiving, let's just give it a shot. Let's just say, okay, so this is what a receiver looks like. You have all of these analog components doing all of this complicated stuff. But really what I'm after is more of kind of a plug and pray approach, where we just take a little segment of wire, plug it into an ADC pin, and maybe something will happen. My dad points out that transmitting is the easy part. Okay, thanks, Dad. But after looking at the data that's coming off these ADCs, he's probably right. Because like if you look here, it's not even just like uniform noise, it's like noise where you can clearly see the ADC is like aliasing and like other stuff, and you're like, ooh, it's probably not gonna work. But I don't know, I just have a lot of determination, so I'm just gonna keep going anyway, and who cares if it's a GitHub project that just goes nowhere. So let's just give it a shot. Let's just see if we just use an ADC, and we can trigger it off a timer so we can have a really precise timing on the ADC. one of the nice things on the CH32 series chips is that they use DMA to save off those samples. So let's just get started with the 003, because I always like to go as cheap as possible, and around 11 or 8 cents if you get in more volume is totally my jam. I was already actively playing with them for the open source tool chain for the CH32V. So yeah, let's just figure out how we're going to go demodulate some RF signals using an ADC. So the first part that you can do is called toggling, or I don't even know, there's probably a better name for it than this, but it's where you pick a frequency and you run the ADC at that frequency, and then for all the, you have some window, and for that window, you take all the odd samples and you subtract them, and you take all the even samples and you add them. And this actually finds half the sampling rate pretty effectively, but sometimes the signal fades away if you're like exactly where like you're sampling exactly where the zero crossings are, you'll completely lose the signal you're after. The other neat part about this is it picks up harmonics, and it's really easy to implement. It's only one add or sub per sample. But we want to do better. We want to be able to actually like receive a reasonable signal, and we don't want it to just fade away all the time. So let's do quadrature, which is exactly like toggling, except it's half the speed. And now we have an in-phase and a quadrature signal where instead of doing plus, minus, we're doing plus, minus, plus, minus, and the quadrature is shifted by exactly one sample. So it's plus, minus, plus, minus, so on. So this tunes to 1/4 the sampling frequency. It fixes the signal fading problem. It's a little bit more expensive, but it also picks up the harmonics like the first one. But why do we get these harmonics? Like, why can we receive these harmonics? So this is the circuit diagram of like the inside of the ADC on the ATtiny85. And one thing you'll notice is that it has this little switch here. And what ends up happening when you have a signal is when you're trying to measure the signal, the switch is only open for a tiny little narrow window of time, and then it does the conversion. And a tiny window of time, and it does the conversion. And a tiny window of time, and it does the conversion. So you're only looking at this wire, at the voltage on this pin for a tiny little window of time. And, well, what if we look at 3 times that frequency? Well, it turns out that exactly where we were looking before, now, as long as we have a little narrow window, we're able to pick up 3 times or 5 times or 7 times that frequency. But why are these signals so weak? So number one is because, well, we're actually cutting out most of the signal. But then number 2 is that there's also this basically a low-pass filter, and we have to charge that 14 picofarad capacitor, so there's very little signal. And so what I did was I just wrote up a little spreadsheet that simulated everything, performed all the operations. I did notice that if you look down here at the bottom, this is like the I and the Q value that the microcontroller would be generating. So if I go a little bit off frequency, they go to 0. So it is actually working. It's able to like tune to frequency, and if I put in 3 times that frequency, it's still working. It's still outputting something. So that's really cool. So let's just give it a shot. Let's write this up in code. Oh, and the power is just the Pythagorean theorem. So it's real simple. So yeah, let's put it in the 003, implement the quadrature decoding. The dev kits for these little guys are like $4 on Amazon. The dev kits actually come with a crystal, which is totally required. And this is a little picture of what I had going here. I had a little BNC connector hooked up to an ADC pin. And that was hooked up to this little receiver here, or little antenna here. So there's no active amplification, but a little antenna hooked up to the little 003 board. And that is connected to this, to my laptop here. And I'm displaying the magnitude of that INQ. And so my friend Frank is around 500 feet now away and using a little handheld CB radio and just sending the carrier. And we're able to pick up just that little bit of signal without any specialized radio anything. Yeah, but this is still kind of annoying because we can only tune to half of the sampling rate. I'd really like to be able to do more. I'd like to be able to tune to any frequency I want. So I started with trying to do FFTs, which we were able to get working, but we had to bump up to the V203, a faster part. It's like 20 cents. I know it'll break the bank. I'm sorry, but we'll get there. There's no floating point unit, but that's really okay because FFTs and most everything else we're doing here is pretty easy to do with fixed point math. It's a lot more operations per sample, so we just weren't able to do it in real time. But I could capture like little windows, perform an FFT, and now you can see that depending on the frequency I'm keying out at, so starts there, and then the 27 megahertz, 27.4 is here, and 26.9 is there. We're able to receive and tune to different frequencies. Now, this is just still not appropriate. I still can't tune to individual things and be able to sample at rate. One of the other techniques is to do correlation with sine and cosine, but it requires a sine and a cosine per sample, which you could do with tables, but it's approximation. But even then, it was still too slow. But then there's this funny little algorithm that people have been telling me about for years now, and I just saw this, and I don't speak math, so I didn't know what to do with it. But finally, somebody just sat down and like helped me through writing some of this code. And it turns out this thing called Goertzel's algorithm turns into pre-computing, which we can do in JavaScript up the stack, some coefficients. And then it turns into taking the sample, adding the coefficient times this value that we have running, and then subtracting another value. And somehow, hidden within this right here, it's doing like this complex phasor analysis, which makes absolutely no sense to me, but it's really simple and it's totally magical. So by the time it's 2024, I was like, okay, that's cool. The other really cool part about this is if you plot a DFT, like a discrete Fourier transform for a single bin, and the Goertzel's output, it is pixel perfect accurate. So somehow this here is doing like sine and cosine and all sorts of complex stuff, and it's only being done with just an add, a multiply, and a subtract. Yeah, it lets us now tune anywhere in the spectrum. I wrote it up into a little spreadsheet to see if I could get it, like, work through all of the logic of it and play with the numbers and make sure that it kind of is doing what I expected, and it did. So I took that, implemented it with some integer math, and so now the discrete Fourier transform, we're friendship's over. Goertzel's algorithm is my new best friend. So what we did is we just took it, threw it into a little CH32V203. These things are 144 megahertz RISC-V. Don't have very much on them, but they do have that. They have a multiply instruction, which is just great, because the 003 does not have that. And it has an ADC, little 12-bit 1 megahertz ADC, which if you just violate the datasheet flagrantly, you can get up to about 4.8 megahertz. It still keeps working. Or 9.6 megahertz, because there's this neat little thing called fast interleaved mode where there's apparently a second ADC where you can like go back and forth. Who knew? But it totally did work. And it's using I guess it's like mine and a bunch of other people's open source development stack for the chip, which rips out all of the different abstractions and just lets you write the code that you're after. It's a little bit more, so it's between 24 and 30 cents, but again, not going to break the bank. The dev kits are only like $10 on AliExpress. And one of the other notes I wanted to do is I wanted to use George Flug's vector scope technique, which is where you take an OLED and you light up exactly 1 pixel at a time. And that's because I didn't have enough time to render out a frame buffer and display it and all of that. But I did have enough time to send the command to the OLED display to say, hey, light up this pixel. OK, now light up that pixel. And so what I decided to do was make it so that it would light up a pixel at a time. And this is what came out the other end, this little vector scope. And you can hear the tuning in the radio. But this is showing on the y-axis the in-phase amount, and on this axis the quadrature amount. And it was able to actually see an AM radio signal nearby. Now, I didn't want to stop there. We have this USB interface in this part. It's a hardware USB interface. I know not normally my jam, but sure. So I had all the JavaScript I was talking about before for calculating everything. Well, we already have that. Well, what if we use the USB and we write a little web HID interface along with Canvas and audio worklet node? And we can then tune FS, so the sampling frequency we're tuning at, tune the frequency the Goertzel's thing is going to operate at, and the window, how many samples we're going to look at once. And mind you, this is the real data from my apartment, from the setup that you're about to see, and this is what we're dealing with. So yeah, let's take a look at, now this is connected by USB to the part. So we can open it, we can start demodulating, and we can select different sampling frequencies, which have different properties. We can then tune, adjusting it higher and lower. So this is the second radio station we can hear.
And you know, over on the Fred Allen Show. And another Allen's Alley resident was featured, John Brown. He was John Doe on Fred's show. And he also later played Digger Odell.
Michelle, 6 to 10 Eastern on ESPN Radio. And our headlines on SportsCenter Online. Paolo Banchero.
So yeah, from my apartment, we were able to receive 4 AM radio signals from just a little bit of noise. And it totally, oops, nope, stop. It totally worked. Hold on. Now, I was curious. I was not able to get an FM demodulator working. I was with Citizens Band, but could not do it with broadcast radio. But my friend Frank and I saw some stations when we would tune to one like 13th or one like a fraction of the FM stations. There was a little bit of noise there. So this is a station that was a couple miles away. It's hard to hear what's going on, but that did not stop Shazam from actually hearing the FM radio coming through on AM. Yeah, so there's a little bit of future work. I hope to be able to do random sampling. When I gave this talk to some of the people in my Discord, they pointed out this thing called random sampling or compressive sensing, which lets you select a frequency that's not where you're looking and effectively violate the Nyquist. I want to play with the whisper. I wanted to be able to do processor to processor. And I want to say thanks to Frank, because he's been hugely helpful in this, everybody else in my Discord. And I really wanted to thank Hackaday and all the people here for all the Hackaday stuff, because they've kind of given me the inspiration or connected me to the people with the inspiration and given me a platform to be able to express all of these wonderful, like, fun things on. Oh, and my dad, yeah, for the encouragement, So, all of the code for this is up on my repo under LoRa, and that's for sending and receiving RF signals without a real radio part. So that's like the LoRa stuff and all of the other experiments, including the receiving. So if you get the hankering to go send and receive some packets from microcontrollers that have absolutely no business doing that, then you too can join the No Radio Radio Club. Thank you.
Thanks very much.